Right, so this is all a bit strange and unusual. This is part 4 in my making of a video, and the video I'm making is 8 bits of image processing you should know. And I've live streamed parts 1, 2 and 3, which is where we looked at the code and the algorithms, and finally we looked at how we tidy up the code. But this one's going to be a bit different, and for a variety of reasons I'm not live streaming it. But this video will be going up on the Javid X9 channel. It'll be completely raw and uncut, and I'm hoping it's not going to be too long. It might be a bit longer than you might expect. And the reason I'm not live streaming it is I just simply don't have enough technology. I tried to get my Chromebook to do the streaming, and the Chromebook was fine with it, but the app that I was using was a Streamlabs app, just seemed a bit unstable. And I didn't want to sort of get 45 minutes in and it shut it down. Also, I'm not really going to be paying any attention to the chat, so it's not going to be a very interactive live stream. And I thought, well, hang on, I'm going to have a camera on me anyway. Why not just upload the footage that the main camera records, which is the one I'm talking into now. So what is this series about? This series has been, it's more of a personal documentary for me to see when it went in the future. I can look back and say, yeah, I spent many hours making videos and this is how I did it. So that's why I'm recording this series. And I think for this video, I don't know how interesting it's going to be. I don't expect it to be a big hit or anything like that. It is purely documentary. But I'm showing it what's and all, what is the process of me making a video, and today we're going to be looking at the recording of it on the screen, and I'm going to get things set up. The only thing that I can't show you how I'm setting up was white balancing the camera, and I have a set of white balancing cards here, which I've just used to calibrate it to give the camera a bit of a warm glow, but it is looking like the camera is a bit low. So I'm just going to put that there, because I've decided that I'm going to do some parts of this video to camera, you know, the sort of and something. I've also turned on my overhead lights. Now that's something I always do because the lighting is consistent with the overhead lights, and I usually close, you can't see it here, but I've got a window right next to me. I usually close, I've got blackout blinds, so I've got control of the light and the environment, and that's a requirement because take something like a Car Crime City video, that could take almost 8 hours to film. Sounds horrible, doesn't it? But in that time, the sun has moved, it's gone from day to night. Sun has moved, flipping heck, come on David, wake up, we're not going to make a very good video like this, are we? It's gone from day to night, and of course all the lighting has changed, and when I'm editing it, when you edit it down to say a 40-minute video, it looks a bit strange when at the start I'm being dazzled by the sun, but at the end you can barely see me. So I like to control the light. But again, something a bit strange today. We're doing a video specifically about image processing, and natural daylight is great for that, because if I use my overhead fluorescence, you'll start to see flicker and the images will be a bit murky. They're not that bright, they're just consistent. Although, as fate would have it, looking outside, it's looking a bit stormy. So I really don't know how this one's going to play out. Fortunately, it's going to be quite a quick video. So I'll just walk you through what the setup is in a video and the preparation that I go to before I start. And if I'm not looking at the camera all the time, I apologise, most of the video is going to be of the back of my head. But I know that this camera, this is a Canon HF-G40, the Legria model, which is the European one, that has quite a good ambient microphone, so it'll pick up everything I'm saying even if I'm not looking at the camera. So all of my voiceover mics, voiceover work is done through this microphone here, which sits about there, and you usually see that on most of the videos. This is on the main screen, and I make an assumption that anything on this screen is what I'm recording. So I have to disable notifications and pop-ups and make sure it looks the way I need it to look, and also take out any kind of personal information. I'm just going to get my chair into the programming position a bit. There we go. And you've seen this application. Hopefully you can see a bit of it on the screen. That's what I'm aiming for. Up here I have my recording software. So this is OBS, Open Broadcasting System or something like that, and that's recording the screen, and it's also recording from this microphone only. It doesn't record any sound sources, so I've got it disabled from recording desktop notifications and things popping up and chimes and bells and that sort of thing. Now normally on this screen I would have my notes, which would be in another text editor showing the code that I'm bringing in. So that's when you see me in my videos sort of bringing in chunks of code, that's where I'm getting it from. It also acts as a bit of a prompt because I don't use a script. That's not a boast, I just feel it's more natural. And it also allows me to make mistakes, and that's a critical message I try to get through on some of my videos, is that you're not going to get this right first time. Sometimes it takes a few attempts. Some of the more stupid mistakes I do tend to edit out, things like typos, that sort of thing, because it doesn't make for very interesting viewing. But if I make a big mistake, let's say I get the semantics wrong, or I fundamentally get the algorithm incorrect, I do tend to leave that in and then go and correct it. For two reasons. One is it shows people make mistakes, but the other one is it gets very difficult to edit, because I edit sort of in a singular forward sequence. I'm not going to be switching off any cameras or any recording, I'm just going to record the whole thing, and then I chop out the bits that I don't want, because I don't want to be editing for weeks. There's probably also going to be a lot of strange, awkward pauses in this particular stream. And the reason for that is I'm thinking about things, what I'm going to say next. Now if I remember, I'll try and verbalise that thought process, but I won't always do it. And then there'll also be things like this, where I go really still, just staring into the camera. And this is me, again, thinking about what I'm going to say to the camera at the time. If I sit there verbalising it, it's going to actually make it very difficult to edit later. I won't know where one thing starts and one thing stops. You'll also see me doing something strange. I've got a Zippo lighter here. Occasionally I'll go like this. And that's to give me a little visual indicator in the editing software, because it'll pop up in the sound accompanying with the videos across both microphones. And that allows it, one, I can use it as a synchronizer, so I can make sure the videos are together. But it also allows me to highlight things that I think are quite important. So usually when I'm recording these things, sometimes I like to throw in a little bit of a sarcastic remark or something. So for example, type, thank you Microsoft, and then come back. That sort of thing, I don't want it to feel forced. I don't want it to, because it isn't forced. I just want it to come across naturally. And today, because I'm using this camera really to make two videos, I need a way again to make a distinction between me just chatting about how I'm making the video and actually making the video. So I'm going to be doing this quite a bit. On the screen I've got my Visual Studio environment set up. I've had a little bit of a tidy up. I'm not the type of person that goes into the bathroom now and puts on makeup and prunes myself. For videoing. I am who I am, this is what I look like. And here I've got my Vimto can, that's an important prop that needs to be seen at all times. And now we have an additional important prop, again definitely no product placement. A very important cup of coffee in a very nice mug. So I'm going to place that right there. And then check in the camera to make sure it's okay. Now I've zoomed out a little bit from normal just so I can make this background video. Normally it would be a bit closer to me and get perhaps more of the main screen in. It depends. I've had a think about some of the algorithms. From the previous videos there was how we're going to describe things and how we're going to do the code, and the intention is to do it a little bit differently than normal. Instead of time, because this is an 8 bits of image processing, it's the image processing I want to get across. I'm not going to do line-by-line code or cut and pasting of things. Instead, what I'm going to do is we're going to do a code analysis, which I've done before, which I've already got the code. I'm going to go into OneNote, power OneNote. Oh, still got the OneNotes from Car Crime City there, so I'll clean that up in a minute. Describe what the algorithm's going to be about, and then we'll show some code for it. And I'm also going to, at the start, indicate that, well, we've already got a platform for capturing the images. I don't want to go into that kind of detail. So I want to keep it specifically about the image processing. Occasionally I'll talk about things that are Pixel Game Engine, but I think we'll start the video with an introduction. Then I'll show the program that I've got that demonstrates the 8 algorithms, what we've worked over the last couple of days. And then I will get straight in with bit 1, thresholding. And I'll show thresholding. Firstly, I'll probably talk about what thresholding is using the OneNote somehow if it's necessary. Then we'll look at the code for it. And all I'm going to do is bring in the code. I can probably do without the diagnostic tools window being so visible here. I'll bring in the code, and we'll talk about specifically that bit of code. So my intention is to do things like, so here we're performing a threshold, and so in this we've got a loop where we're going through all of the pixels in the image, and we're just setting the output pixel of an image on the thresholded value of the input. And you'll see I'm already starting to stutter and make mistakes, and this is because I don't have a script. And we'll see how well that goes. So it might not be the most entertaining YouTube video to watch once it gets started, but as already said, my disclaimer is it's not really a public consumption video, it's more for a personal documentary about what it is that I'm doing. For no other reason than I'm probably quite arrogant, I suppose. Anyway, I think we're probably already at the starting point. I just want to do a quick light level check because I've been wanting to try the median, sorry, not the median filter, the adaptive threshold algorithm that I've been showing, because I don't think it's been shown very well, and I've been trying this. So if I'm going to use it, I'm going to compare it with the normal thresholded one. Now you can probably just see that up here, and of course you'll see this in the final video. But in the normal one, if I bring in some shadow, so we can see the thresholded image, but my hand is shadowing the text on the document. But if I go to the adaptive threshold, we can see that my shadow doesn't affect it finding the text one-lone coder. So I think that's quite a nice, compelling example of why an adaptive threshold is a useful thing. So that's quite nice. Median filter. I think for median filter I've created another prop in my notebook, which is just the words median filter. Again, you probably can't see it as close up as you'd like, but there's some noise on there. We'll get to that later on. There's a good chance that during this video I'm probably just going to completely forget that I'm making this documentary video and stop talking to the camera. That's because I really do like to try and focus on what I'm doing, and another reason why I think the live stream chat will probably make this a very long thing. I do anticipate, if all goes well, it's probably going to take about 2 hours to do. Nicely, I'm not writing the code, there's not going to be very much code editing, it's mostly going to be vocal editing. But there will be some times where I've just got to think about what it is I'm doing with Onenote. I think I've covered everything I need to talk about. Oh, things I haven't mentioned, so here is, I have a Wacom Intuos 4 tablet, which is where I use my drawing stylus for the Onenote stuff. I'm getting better at doing that, even it's drawing here but looking over here. All the setup is exactly the same as we've seen in the previous streams. I think we're good to go. So, with that in mind, I think I'll just have a quick slurp of coffee, because this is quite unusual for me. I usually have some a bit of a pre-video making ritual. There's a song that I like to put on, but if I put the song on, YouTube will mute it or copyright claim it or something like that. So I'll not do that, and that will forever be a secret which song that might be. Right, so just going to do test 1, 2, 3. So what I'm checking here is that my voice levels for the boom mic are on average in the yellow and that I'm not peaking. Down here I also have, I know you can't really see, but down here I also have quite a sophisticated set of sound inputs, which have got LED indicators on to tell me if I'm clipping or not on the microphone. I'm using an XLR phantom powered, is it cardioid mic, something like that, I don't know. Anyway, it's nice and cheap on Amazon, but I think the sound quality is quite nice. I've no particular webcam recording going on today other than the one that I'm using for the video itself, the source images, so that's quite nice. I've mentioned I've already white balanced, and I think we're probably good to start. So yeah, let's get stuck in. There'll be lots of moments like this where I'm thinking, right, what do we do next? I think for a background, because I've got to think, I'm now going to do sort of an introductory explainer of what the video is about, but I think in the background, perhaps something like that, it's a little bit more interesting for the viewers. And I did mention I'm a bit more zoomed out than I normally am. Let's make sure I can get into a position where I can rotate my chair. I've chosen a suitably geeky t-shirt because that's what people tend to expect now. And if I'm looking, doesn't look like I'm looking at the camera, it's because I'm looking at the video feed. The camera has a little side screen sticking out, and I can see myself where I am relative. So when I'm looking at the camera it's like this, but sometimes I'm looking at myself in this little side screen. The camera is equipped with about 6 hours of recording time, and it'll record at full HD, and I record all of my stuff at 25 frames per second. I don't see a need to go any higher for this sort of thing. Also, if I had that much data, the files would become unwieldy to edit later on, which is, it's all great saying we need 4K this, 4K that, but then you need a computer which can handle all of that stuff, and I don't have it. Right, so we're good up there, we're good there. It's getting a little bit gloomier outside. I'm hoping the light doesn't start to really upset what we're trying to do. Right, so little synchronizing pulse. This is where I'm going to sit and think about what is the introduction that I'm going to give. Now, I want to cover things such as image processing, but why should programmers and why should people be interested in image processing? And then I also probably want to include a disclaimer that I'm not trying to optimize this in any way at all, because there are existing libraries that people can use. I just want to demonstrate the concepts and how simple some of the algorithms are conceptually. Probably take a few attempts at getting the intro right. And sometimes I also like to edit myself, so you'll see the jump cuts. So there'll be times where I go, hello, blah, 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 and there'll be a pause in between. And that's because I'm thinking about what I'm going to say next. Let's see how this sounds. Oh, before one very important thing before I forget, I actually need to make sure I click record on the desktop software, don't I? That would have been a problem. So start recording. So this is just recording to disk now, and when I'm recording to disk, I record at a higher quality than I do when I'm streaming. I stream at 720, but I record at 1080. Okay, so that's recording. So now that's recording. Now I can sync. And I think we'll just get going. So I just need to get into my head that we're just going to do this naturally. It's really unnatural thinking I've got two videos being filmed simultaneously. One more. Let's get going. Hello, and it's been, see, already a bad start. Hello, it's been a while since I've done one of these, but I think it's time for another 8 bits of video, and this particular video is going to be 8 bits of image processing you should know. And you might be thinking, well, why do you need to know anything about 8 bits? Hello, it's been a little while since I've done one of these, but I think it's time for another 8 bits of... Dear me, yeah, horrible. It always starts like this. I've got to get sort of into the flow. Let's try again. Hello, it's been a while since I've done one of these, but... Oh, flipping heck. Hello, it's been a while since I've done a video like this, but this video is 8 bits of image processing you should know. And you might be thinking, well, why do you need to know anything about image processing? Well, it's quite a useful technique in quite a few different scenarios. Image processing is fundamentally operating on 2D arrays of data, shaping this data in ways that make more sense to your application. And even though it's got the word image associated with it, it doesn't necessarily have to be about images. So in the past I've used image processing techniques for procedural generation, for example, in games. Of course you can also use image processing techniques in graphics applications. On the whole, image processing is just a useful thing to know. It's one of those tools you should have in your... On the whole, image processing is just one of those useful things to know. It's one of those tools you can keep in your toolbox to help you... No, I don't like where that's going. Let's try again. I think it's also too long. Hello, it's been a while since I've done one of these videos, but this video is 8 bits of image processing you should know. And you might be thinking, well, why do you need to know anything about image processing? I'm a programmer. Well, images are just 2Ds of... Oh dear me, this is embarrassing now, getting off to a bad start. Trust me, it'll start to flow once I get going. Hello, it's been a while since I've done one of these videos, but this video is 8 bits of image processing you should know. And you might be thinking, well, why do I need to know anything about image processing? Well, images are just 2D arrays of data, and the algorithms that we apply to this data can shape it in useful ways. Obviously, some of the applications involve images and cameras and video footage, but there's also other ways of manipulating 2D data to your advantage, for example in things like procedural generation. On the whole, I think image processing is... On the whole, I think most programmers should have a... Yeah, that's good. On the whole, I think most programmers should have an awareness of image processing. It is a very useful tool to have in your toolbox. So let's get started. Okay, I think there's enough there for an introduction. I will cut out some of the pauses, but I wanted it to flow, that's why I repeated the whole thing. I'm feeling a little bit more comfortable now too. Just a bit unusual knowing that people will be watching all of these mistakes. It's sort of playing on my mind a bit. So at this point, I usually like to show, get the chair in the right place, I usually like to show what we're going to be developing in this application, in this video. Before I start, I'm going to show you the application that I'm using to demonstrate these 8 bits. Before I start, I'm going to show you the application I'm using to demonstrate the 8 bits. Just waiting for the coffee to settle there. Before I start, I'm going to show you the video that I've created to demonstrate the 8 bits, and it's quite nice because it allows us to quickly compare the algorithms. So here it's going to show the first bit, which will be thresholding, and we can choose different numbers to look at the different algorithms and see what their effects are. Because it's working with video, you can see here's a live feed of my arm waving around, I think it makes quite a nice interactive tool which is great for learning. But this video is going to be a bit different to some of my others. I'm not going to go through it line by line from scratch. I've already created the code, and what I really want to emphasize is what is the image processing that is going on and how does it work. Okay, that's good. I think that'll work. So now I want to go into OneNote and introduce the bits. So I'm going to draw a title card. But I need to get rid of all of the car crime city stuff that we were doing for the last video. So Control A and delete, and that's the red blob. The red blob of whatever it is, I can't delete it for some reason, but it's always there. And now I need my stylus, wherever I put it, there it is, that's good. Right, so I need a title card, so I'll choose the right pen. Now this is the kind of stuff that I would edit out normally. You don't want to see me just come up with these ideas. And I've got to think, do I want to make life easy for myself or hard for myself? I could choose to just put the title of what the bit is and then say bit 1, thresholding. Or I can create a more fancy looking title. I think in this case I'm going to keep life simple for myself because I want it to be clear and sort of a good explanatory video. But we'll definitely start with bit 1. Thresholding. Bit 1. This is the process of binarizing an image. Here I have an image. I'm going to assume it's a grayscale image, so the pixels go from black to white. Thresholding involves taking an individual pixel and classifying as it. Thresholding involves taking an individual pixel and classifying it as being above or below the threshold. If it's above the threshold, you output 1. If it's below the threshold, you output 0. This green line represents a single row in our image. I'm not going to use the word luminance there, I'm going to use the word brightness instead, because not everybody, different languages and things, will fully understand what luminance is. If I take this row and plot its x position against the brightness of that pixel, I might get something that looks like this. Thresholding involves specifying an appropriate value to act as a cutoff. So any pixels above that value will get classified as 1 and any below it will get classified as 0. The red dashed line represents my threshold value. So now with my blue pen I can indicate what the binary equivalent of this might be. So it starts down here at 0, but that goes above the threshold to 1. Below the threshold, above the threshold, and we've binarized our image. Right, I think that's clear enough. Thresholding is very simple. I'm also aware that I want each of the bits to only be 3 or 4 minutes long max, but with this first one I need to do a bit of explanation of what's going on with the rest of the code. So I'll close that down and then I'll introduce the program. To demonstrate these programs, I'm using a Pixel game engine application that I've already created. And I feel it's necessary to give you a brief overview of what this application is before we get stuck into the algorithm code, just so it makes some sort of sense. Fundamentally, it's based on the idea of a frame, which is a fixed 2D array of pixels, in this case 320 by 240. The pixels are floating point type. So instead of working with RGB values, I'm taking the RGB from the camera and converting it to a floating point value between 0 and 1. By converting to the floating point domain from the integer domain allows me to avoid complexities such as integer division. This simple frame class has some accessors, get and set, which will do boundary checks for me. So I can quite happily set a pixel's value beyond the edges of the image, and if I get something from beyond the image, it just returns a black pixel. So 0 is black and white is 1. My frame class also overrides the assignment operator. So I can have multiple frames in my application, and I can transfer the contents of one frame to the other with ease. For this video, I'm not going to dwell on the image capture side of it. I've done quite a few. For this video, move that back. For this video, I'm not going to dwell on the image capture side of things. I've already done that in other videos. And it's enough to say that we simply use the escapy library to capture a frame from a webcam. So in onUserCreate, the webcam is initialized. And in onUserUpdate, I capture the image from the webcam per frame and convert the pixels to floating point and store it in a frame called input. This program shows 8 different algorithms. And so the bulk of the code shown here handles the selection of which algorithm is currently being demonstrated. And the algorithms also have a degree of user input, so we can change values to see how they change. And the algorithms also have a degree of user input, which allows the user to change the values to play with the algorithm and see how they respond under different circumstances. For example, when the user presses the 1 key on the keyboard, it changes the current algorithm being demonstrated to threshold. So let's continue looking at that algorithm. Here it is, and you'll see this on most of the algorithms. We do a little bit of user input if there are values to change, and then we actually perform the algorithm under demonstration. And thresholding is very simple. For all of the pixels in the frame, we read the input value of a pixel for that location, compare it with a threshold value, which will give us a 1 or a 0 in response, and then we write that to an output frame. At the end of the program, I then draw the input and output frames. Hopefully you can see thresholding is very simple indeed. So let's take a look at it. This is thresholding. Now my webcam has some automatic gain correction, which is what you saw then as the image sort of changed and faded. I can't override those settings using the API for the camera. But for this video it doesn't really matter. I'm in threshold mode now, and we can see the input image here on the left is in grayscale, but the output image here on the right is in black and white. It's been binarized. And it says here I can use the Z and X keys to change the value of the threshold. So currently it's at 0.5. It's halfway between the minimum and maximum intensities for the grayscale. As I increase the threshold value, we see less pixels being attributed to a binary 1. As I decrease it, we see the opposite. Thresholding is essentially the coarsest of filters. And it is usually the first step in removing as much rubbish from an image as you can. For example, here you can see on the notebook the text one lone coder comes through quite clearly, but the lines and the slight greyness of it doesn't. So if we were then to go on and extract this text, for example, it's much easier now. We're not contaminated with this spatial background noise. We've thresholded it out. Okay, so I think that's probably sufficient for that one part. And there's not much to a threshold, it's simple. I also quite like the flow there. I'm not bringing in code, I'm just talking about the code. That might get some strange responses from the audience because they won't be, some won't be used to seeing it that way. But I really don't want to make a really long video, and some of these things are going to require probably a few attempts at getting right. Okay, so now we can move on to bit 2, which is motion. I'll draw the thing. Ooh. Black pen. Bit 2, motion. And for this video I'm assuming the simplest kind of motion. We won't be able to get any direction information from this. The word motion implies that something has moved. And for something to move takes time. So to detect motion in an image, we need to allow time to have elapsed. Fortunately, with video, this is quite simple, because a video camera returns successive frames in time. Which means we have a built-in delta time between each frame. Alongside movement in time, motion also implies movement in space. The object was in one location and now it's in another. But for this bit, let's not think of objects as being the things we're looking at. Instead, we're looking at pixel grayscale values. So over time, I'll put an axis in. So over time, if something is moving in the image, a particular pixel value is also changing. So we can identify that motion has occurred by looking at the difference of pixel values between successive frames of video input. And so on this graph, we can see that the difference between A and B is related to the change in that grayscale value. The end result of this could be signed, and in some applications that's a useful thing. It gives you additional information. But for our application, I'm just going to take the absolute value of this to tell us that motion for that pixel is likely to have occurred. The code for motion detection is equally as simple as thresholding. I'm going to go through every single pixel in my frames with these nested for loops. And I'm going to look at the difference between the current frame and the previous frame by subtracting them, and then taking the absolute value of that result and setting that in the corresponding location to the output frame. I then draw the input and output frames. I update the previous input frame before I acquire a new image in the input frame. Here's the algorithm running, and it's looking at a reasonably static scene. But as soon as things start to move, I bring my hand into the scene, we're looking at the difference between one frame and the previous frame. But we only see illumination in the output where there has been change, so that signifies that motion has occurred in those locations. Because the frame rate of my camera is reasonably quick, it's about 20 frames per second, I get what looks like an edge around the object that's moving. But don't be fooled by this, it's not strictly an edge, although you can use it as an edge. It is just the difference between the two frames. A useful application of this is to motion detection like this is usually a foundation algorithm. It is used to guide your decisions in subsequent algorithms that you apply to the image. For example, I might want a system to shut down if nothing in the scene is moving. I mean, why bother taking more images if nothing has changed? So I could detect that by accumulating the sum of all of the pixels in the output image and then checking that against a threshold value to tell me, has there been enough motion in the image for the system to switch on? Yeah, I feel that one went quite well too. It's simple enough. I think it was described in a, I hesitate to use the word elegant enough way, but I think it gets the point across. These things, when looked at like this over a long period of time, you might think, well, hang on, I can't remember the bits I've just said, or it doesn't make much sense in the context of this making of video. But once we've started to edit it all together, it becomes a much more smooth experience. It tends to flow a bit better. Right, what was bit 3? I think bit 3 was low pass filtering. So this is where things start to get a bit interesting. So I have to explain a bit of science. So I need to have a think about what it is that we're doing with low pass. Back to the Onenote. See, how long have we been already? Difficult for me to tell on my camera. I think about 45 minutes, something like that. Oh, look at that, just fits in. Now, how am I going to actually draw this one is a bit trickier. Let's just have a quick run at it. Basically, it's taking motion. No, it's not really. Well, it kind of is. It's kind of taking the motion image and using the amount of difference between those two frames. See, the actual mechanics of implementing this is very simple, but then describing it in such a way that somebody can just understand sort of intuitively, if they've never heard of RC time constants and all that sort of thing, is what we need to think about. So I think what we want to do is, I just want to start sketching something out there. We've got a pixel value that changes per frame. Something like that. The end result we're after is something like that. So we're removing these high frequency change components. And we're doing this by essentially saying that an activity register is updated with the difference of the input minus the activity register itself times by some constant. So if this section here is very small, then the change to the activity is very small, and if the change here is large, the activity change is large, and we can regulate that rate of change using this constant. Okay, let's have a think about it like that. Bit 3. Low-pass temporal filtering. As we've just seen in bit 2, the value of a pixel changes over time. And if we look over a longer period of time, we might see that the pixels change values quite rapidly between frames. This is called noise, because sensors aren't perfect. Lighting conditions, electronics, and all sorts of things can influence the value of a pixel. This noise can cause us problems, because what we actually want to see is the real value of the pixel change over time, which is indicated by this green line. We can approximate that that's somewhere in between all of these noise values. The noise can become a problem if you do things such as thresholding, because the noise might just tip you above or below the threshold inappropriately. We effectively want to run the grayscale value of the pixel through a low-pass temporal filter. So the low frequency component of the pixel is allowed through and the high frequency components are removed. We can approximate this with a very simple equation. For a given pixel value, p, we're going to update that pixel value by looking at the difference between the input pixel value and the current pixel value and multiplying that by a constant. I drew my tau incorrectly there. And multiplying that by a constant. Fundamentally, if this distance is small, then the change in our output pixel is small, and if it's large, then the change in our output pixel is large. But we can regulate that change with this constant. I think that'll do. Let's have a quick look at the code. I'm just going to change that to pixel and that to pixel. I think that reads a little more clearly. In engineering, this is also known as an RC filter. And its implementation is very simple. In the low-pass section of the program, I'm doing some user input so I can change this constant value. I'm doing some user input so I can change the value of this temporal constant. And then I iterate through all of the pixels in a frame. I look at the difference between the input and the output. I scale this distance with our constant value. I scale the difference with our coefficient. I scale the distance with our temporal coefficient. Oh, come on, David. I don't even know what I just said then. I scale the difference with our temporal coefficient, and then I accumulate that difference back into the output frame with this plus symbol. For this algorithm, the output frame is persistent between updates of the video camera feed. meaning that output pixels are only changed by a small amount depending on how large the change was of the input. So here in the program, I'm now running bit 3, the low-pass temporal filter, and the two images look very similar. It might not even be that possible to see on the YouTube video, but the input image on the left actually has quite a lot of per pixel noise, but the output image on the right has no temporal noise visible to the naked eye. If I move my hand into the scene, this is a particularly slow filter. So I can make rapid changes sort of by wiggling my fingers around here, but we can see that the output image doesn't change very much. It's ignoring those fast changes, only allowing the really slow changes. If I leave my hand in a fixed position, eventually it feeds into the image. So this is exaggerated in a way. I can use the Z and X keys to change the value of this constant. So I can make it very slow indeed, which might not immediately seem a useful thing to do, but if you wanted to do some background subtraction algorithms over moving images, this is quite a nice way to do it. You can accumulate the background of an image over time and then use that as a way to isolate things in the foreground. If I increase the value of the constant, it becomes far more live. Let's keep going a bit, until the two images look very similar indeed. But if you get it too high, this constant, you'll start seeing the per pixel camera noise coming back into the output image. So, low-pass temporal filtering is a great way to filter noise. And it also looks all ghostly and cool. Right, what's the next one? Right, so this is the biggie. The convolution and erosion are the two that I'm worried about doing the most, because they do require a bit of thinking about why they're doing what they're doing. I just want to make sure, oh dear, pressed the wrong button. I want to make sure I can get all of the code on the screen. Convolution. Let's just take that out. Saves us a few lines. Put that one back in. Convolution. Are we on bit 4? Is it bit 4? Bit 4. Bit 4. Convolution. Whereas the previous two bits have looked at filtering things in the time domain, convolution looks at filtering things in the spatial domain. Fundamentally, we're going to decide what to do with a pixel by looking at its neighbourhood. For this example, I'm going to look at the immediate 3x3 neighbourhood of our target pixel. And this neighbourhood is called a kernel. And you can think of a kernel as a template of coefficients. That are used in a dot product of the neighbouring pixels in that region and values of the kernel to give us a result for the central pixel. So my kernel might be defined here as a 3x3 matrix of values. These values are overlaid over the corresponding pixel in that location. And we also include the central value, which is the target pixel. I can give these kernel values location information to identify their relationship to the target pixel. I work out my final pixel value by performing the dot product between a kernel coefficient and the grayscale value of the pixel at that location. So this component, for example, is this component of the kernel multiplied by this pixel value. And we go on to go through all of the kernel locations. And so what effect do you think this kernel might have then? Well, we can see it as being regions of influence. We're strongly influenced by the target pixel, the one in the middle. But we're also a little bit influenced by our immediate north, south, east and west neighbours. Conveniently, in this kernel, all of these values add up to 1. And this is quite deliberate. So we take the bulk of our pixel's value from what it already is, but then we take a little bit from its neighbours, but we still land within the approximate range for that pixel. This will give us the effect of blurring the image. Because we go on to apply this kernel for every single pixel in the image. I've implemented convolution in a really naive way. Here I'm going through every pixel in the frame. And for each location, I'm accumulating into an fSum variable. My kernels are 3 by 3, but I want to get the corresponding offset location for a kernel coefficient in my image. So I've got an additional 2 nested for loops, which iterate through the values in my kernel. The kernel we've just created is a blurring kernel, and I'm representing that as just an array of 9 floating point values. I index into the appropriate location of that kernel using some simple 2D to 1D arithmetic. Once I've got the right coefficient, I multiply it by the input grayscale value and accumulate it into my fSum variable. I then set my output pixel for that location to the fSum variable. In this demonstration, I've included 2 kernels, blurring and sharpening. The mechanism for convolving the image is exactly the same for both, but the coefficients of the kernels are quite different. There's a little bit of user input at the top to choose which kernel we're going to apply to the image. Here I've chosen the convolution component of the program, and we can see the input image on the left is nice and sharp, but the output image is ever so slightly blurry. I might be able to enhance that. Start that again. In the demonstration program, I've chosen bit for convolution, and it's currently running the blur In the demonstration program, I've chosen bit 4 for convolution, and it's currently running the blurring kernel. And we can see that the input image on the left is sharper than the output image on the right. This blurring only occurs once over a 3x3 neighbourhood, so it's a very delicate blur. However, if I press the X key, I can change to the sharpening kernel. And we can see that this kernel has the effect of enhancing any areas of high contrast in the image. You may have seen these filters in popular art programs. The downside to sharpening, of course, is it also sharpens all of the noise. So we may want to combine convolution with some of the previous filtering algorithms we've already seen. In this simple demonstration of convolution, I've used a very small kernel, 3x3. But there's 4 lots of nested for loops in implementing this. So if you increase the size of your kernel, suddenly there's a lot more computation to perform. Another approach is to repeatedly apply the convolution kernel to an image. So for the blurring, for example, if I then convolved the blurring image with a blurring kernel and then did it again and again and again, the image would get more and more blurrier. I could use a larger kernel too to cover more area, so the surrounding pixels influence my target pixel over a wider area. I'm going to start that again, and I kind of know what I want to say, but it all came out a bit scrambled. In this convolution example, I've used a very small kernel, 3x3, so it can only look at its immediate neighbours. For blurring, for example, if we wanted to have more of a blurry image, there's 2 ways to go about it. The first is we could repeatedly blur the image, so once we've blurred it once, we then use that as the input and blur it again, and again and again and again, until we've got the desired level of blur. The second approach is to use a much larger kernel, so we can go 5x5, 7x7, 11x11, whatever you want. But the kernels and the convolution I've shown here are 4 levels of nested for loops. They will explode computationally and become very slow and difficult to get any kind of real-time performance. If you're serious about doing convolutions, and most image processing techniques and programmers are, then you'll want to do your convolutions in the Fourier domain, the frequency domain instead, where you take the fast Fourier transform of your input image and your fast Fourier transform of your kernel, combine them, and then take the inverse Fourier transform of the result. And this will allow you to get very large kernels with a fixed computational overhead, a far more suitable approach for real-time image processing. So obviously I did a bit to camera there. It was a little bit sort of ad hoc and made up, and that's why I wanted to click it, because I feel one of the things that people will say is, oh, you can't do kernels with much larger sizes. Well, I know that, but I also want to demonstrate, firstly, I know that, but then also don't make a point about highlighting it, because that could alienate beginners very quickly. So it's important to get those things in. Right, so convolution we've done. What was next on the list? I think hopefully is it just Sibel. I lost my list of things. So Sibel, yes, Sibel. So we're halfway through. Good. We're not doing too badly. Because Sibel can go very quickly. Blue again. Bit 5. Sibel edge detection. Detecting edges in images is perhaps the most useful thing to start. Oh, where am I going with this? Detecting edges in images is perhaps the most useful thing. Edges in images detect. No, hang on. Start again. Edges in images indicate where the information of an image is. Simplistically, because edges indicate where spatial change has occurred. In this example image, we have background and we have a box. The background doesn't change locally and the box doesn't change locally. So there's no relevant information in either of those zones. So one could argue that the box is really only defined by how it is different to the background. And this difference lies along the edge of the box. So detecting edges is quite an important step. And perhaps the most classical way to detect edges is using Sibel's edge detection. Which is a pair of kernels used in a convolution. The two kernels detect edges in the two main directions. We've got horizontal, the kernel looks something like this. And we've got vertical. If we convolve the image with the horizontal kernel, we will see the horizontal edges. And then we'll convolve the image with the vertical kernel and we'll see the vertical edges. We'll then combine the horizontal edges and the vertical edges into a single output image to show us all edges. As before with the motion detection, the sign bit of the result of these convolutions can contain useful and interesting information. But I'm going to throw it away by taking the absolute value of the results of these convolutions. This happens sometimes with Onenote, is the cursor gets confused as to what it should be. You need to right click somewhere, there we go. The Sibel part of the code is exactly the same as the convolution part of the code before, except I'm doing the two things at once. I'm maintaining two summation variables instead of the one. And when I'm writing the output summation, I'm taking the average of the sum for the vertical and sum for horizontal components. I've defined two additional kernels in exactly the same way as I did before. Now, interesting thing, I've just looked at this code and see that for horizontal lines I seem to have the vertical kernel, and for vertical lines I've got the horizontal kernel. So I'm just going to change that around, fix that up, and redo that section, just redo that little bit. Then it's making me think, have I done that right in the Onenote? So Onenote horizontal should be, yeah, 1, 2, yeah, so that's okay. I've defined the kernels for Sibel in exactly the same way as I did before. They're just arrays of floating point values. Let's take a look. Sibel edge detection. Here is the demonstration program running the Sibel edge detection algorithm, and as we can see, edges are illuminated and boring surfaces, i.e. those that have low frequency spatial information, remain black. The nice thing about Sibel is it works on this grayscale input, and you can see it starts to highlight all of the areas of high frequency information. So look at my really hairy arm there. It's quite a visible thing, so that's really indicated texture. I think that's all I'm going to say about Sibel. I know in the previous videos we looked at sort of artificial bump mapping and all that sort of thing. I don't think that's necessary here for this video. Right, so let's move on. What are we up to? My list of algorithms. Convolution, Sibel. Oh, morphological operations. This is kind of the one I've been dreading a bit because it takes a bit of time to explain what's going on, and it's even more time consuming to explain why it's useful, and the visual demonstration I don't think is particularly compelling. But either way, so we're up to bit 6, is it? Bit 6, morphological. Yeah. Okay. Draw bit 6. Bit 6. Morphological Operations. Even though that sounds like a mouthful, morphological operations are really a study of how things look spatially in the image. We want to do things regarding the shape of objects in the image. And we do this by working in the binary domain. So we must threshold the image first to binarise our pixels to 0 and 1 values. And for this bit, it's really split into 3 different bits. The first I'm going to look at is called erosion. In this simple demonstration image, I'm assuming that the background is 0 and my object is 1. Erosion is the effect of eroding a single pixel off all edges of our object. Effectively shrinking it. And it's useful to remove erroneous, spurious pixels from other stages of image processing. Because if I had a single pixel like this, or a cluster of single pixels in a line, and I eroded it, then if we're removing a 1 pixel from all edges, it's going to disappear entirely. Whereas larger objects, the morphology remains intact. The opposite to erosion is dilation. And it is quite literally the opposite. This time we grow a 1 pixel boundary around our shape. So just going back to the previous example, if we had some spurious small information and we first erode it to remove it, and then we dilate the image again, there's nothing here to actually dilate, but our original shape will go back to something very similar to how it was originally. So this is a nice way of removing spatial noise from an image. In many ways, implementing morphological operations is very similar to convolutions, but this time we use logic instead of dot products. Looking at erosion, we use a very similar 3x3 kernel to how we used in the convolutions. But this time, my kernel is just going to be a 3x3 matrix of logic 1s. For every pixel in my source image, I overlay my morphological operation kernel for that pixel. So let's, for example, say I put it here, centered around this pixel. I then do a logic AND with all of the elements in the kernel and all of the elements in the image. In this case, we can see that 1 and 0 here is, well, 0. And this one's going to be 0, this one's going to be 0, and once we've ANDed all of those together, the end result is going to be 0, because we've got some zeros in there. So I will write to my image 0. However, when I get round to operating on this section of the image, the result is a logic 1. Because all of the kernel coefficients and all of the surrounding neighbourhood pixels are going to AND together to give me a 1. This pixel that was on its own has been eroded, but this pixel that is robustly supported by its neighbourhood stays intact. Instead of just doing logic AND, we could also do some simple arithmetic. We could count how many of our neighbours are equal to 1 and come to the same conclusion. So in this case, I've got 8 neighbours, all equal to 1, so my current value pixel is a 1, but in the original scenario, only 3 of my neighbours were 1. So I could then look for less than 8 neighbours, and in that condition I set myself to 0. Now the interesting thing with erosion and dilation. Now the interesting thing with erosion is that one man's erosion is another man's dilation. If I inverted all of these bits and applied the same kernel, I would have the effect of dilating the image. But I can also dilate in a second way, without requiring this inversion. And this one is quite simple. If a given pixel exists, then set its neighbours to exist as well. And this would have the effect of growing our object by 1 pixel along all edges. Before I get stuck into the code on this one, I just want to show visually. Before I get stuck into the code on this, I just want to show visually another useful thing for dilation. That if I can identify a particular point on an image, let's say here, and I repeatedly dilate, I can effectively flood fill in the image. Now, there's an important condition here, is that after every dilation, if we logically AND that with the original image, we'll never go beyond the boundaries of the original image. So this allows me to fill a secondary image with just the space occupied by a single shape in binary space of the input image. And this is a great way for doing image segmentation, the extraction of objects or labeling image parts. In fact, I find this to be really interesting, and I think it's worthy of a video in its own right. I've got some interesting examples of how we can demonstrate that, so expect in the near future a follow-up video to this, just showing morphological operations. In the code, the morphological section is the largest of them all. It's got a great degree of user input, one to select which particular dilation or erosion operation we're going to do. There's also a third one called edge, which I'll talk about when we get to the code. But I can also control the number of times that I perform the dilation or erosion, and so we'll be able to see those effects visually. But the first thing and the most important thing is we need to take our image from the grayscale domain into the binary domain. So I'm just thresholding it, and I'm going to threshold it using the value that we've specified in the threshold algorithm. So this will allow you to tweak the threshold first. Then we go on to choose dilation, erosion, or this third one, which I'm calling edge, because it's going to be an edge detect using morphological operations. For dilation, it was simply a case of seeing if given pixel value is equal to 1, then set all of your neighbours to 1 too. Easy enough. But I use this third register activity because I don't want to alter the frame as I'm going through the pixels. It's important that the whole frame is treated homogeneously. It's important that the frames are treated homogeneously. For erosion, rather than doing a set of logical operations, I decided to go with the summation route. So I'm looking at all of the values of my neighbours, and all of the ones that are 1 I'm summing together. Now, I know that in my activity frame they're going to be 1s or 0s anyway. We've binarised the image, so I'm just going to add them. And I'm going to check to see if my activity is 1, and if it is, but not all of my neighbours are set to 1, then I'm going to set myself to 0, put myself out. This third one, which I've not drawn up in Onenote, I've called edge, and it's exactly the same as erosion. But instead of looking for less than 8 neighbours, I'm looking for precisely 8 neighbours. So in the situation that I am an illuminated pixel, and I have all of my neighbours, I'm going to extinguish myself. So let's take a look. The program is started up with the thresholded image, and this is just so I can tune the threshold value appropriately. I can still tune it later on, but it's just a bit easier to do whilst looking at the grayscale image. Then I'm going to choose bit 6, more binary morphological operations. Now the current operation is dilation, and it looks like there's just a single iteration being applied. So on the left, where these individual pixels are occurring, you can see they're expanding into a 3x3 region. This has had the effect of removing the one lone coded text entirely from the book object. So this might be a precursory stage in being able to extract where is the book this time, if that's useful. I can increase the count. I can increase the number of dilations with the A and S keys. And as you might expect, the regions just grow. So dilation is a way of grouping things together. Erosion is a little different. Here on the left, those spurious single pixels have all but disappeared, as has a lot of the noisy background, so erosion has really just allowed us to focus on the core parts of the image. If, for example, I eroded this image and then dilated it, well, I can't bring any of that background noise back in. We're looking at the eroded image now. If I dilated this, there's no source pixels to seed anything for dilation. So combining these two operations is a nice way to remove noise. Let's add multiple erosions, and eventually we can erode the image away entirely. Erosions and dilations, as I demonstrated very briefly, can be used for detecting and labelling objects individually. And in a primitive way, they can also be used for sizing objects. If you continuously eroded the scene and looked for the finally illuminated pixel, you could then dilate that pixel and logically and it back into the scene to highlight the largest object. So you could use erosion and dilation for sizing too. Now finally, there's one more mysterious one. If I press the C key, and that is using morphological operations to detect edges. And this gives you a really nice edge detect where all of the edges are a single pixel. If I bring my hand into the scene, it's a bit messy, let's find a nice high contrast scene, there we go. So that's quite nice, we're isolating all of the buttons. Now you can see the camera is adjusted in gain there, not much I can do about that. But this is different to Sibel in that it gives you a really crisp outline edge for an object. Phew, right, we're getting through it. Just keep going. How long have we got left? So I think we've been recording for about an hour and 45 minutes, something like that, maybe a bit longer. I can't really tell. So the next one is median filtering. So median filtering is a bit easier now. I think we're on the home stretch. So this will be bit 7, I hope. And I have a prop ready for median filter, which is this one. I'm just hoping we're not running out of sunlight. I need to be able to cast shadows later. So is it bit 7? Let's just double check. There's my list, yeah, bit 7 and then adaptive threshold is bit 8. So these are the two oddball ones because they're not really techniques that we've seen before. There we go. And bring up the Onenote, so bit 7, median filter. Bit 7, median filtering. When working with real-world sensors, things don't always go to plan. Sometimes your image will have little tiny artifacts in it. These are bad pixels or snow, depending on, it might be in a radioactive environment for all I know, but you end up with something which doesn't look quite right. And these are usually quite tricky to filter out, unless you use a median filter. Median filters are conceptually very simple. In a similar way to convolution, for a given pixel, we look at its immediate neighbourhood. In this example, I'm using a 5 by 5 neighbourhood. And we're going to make an assumption in our image that we're not really expecting spatial change to happen over a single column of pixels or a single row of pixels. That's quite unusual in natural images. So it tends to be that in general, information in images is rather blurred out across the image. So up here, where I've got this single erroneous pixel, I can make an assumption that most of my image in that region is behaving one particular way, and that this black pixel is some form of outlier. And we can statistically remove the outlier by looking at what the median pixel value is across all 25 pixels in this 5x5 kernel. Now, if you don't remember what the median is, you take all of your values and you sort them in order, and you take the one that lies directly in the middle of that sorted set. It's one of those quirky mathematical phenomena where it sounds really complicated mathematically, but there's actually no maths involved at all. It's just a sorting and an extraction. For the median filter code, as usual, I'm iterating through all of the pixels in an image. Start again. For the median filter code, as usual, I'm iterating through all of the pixels in the image. And I'm not trying to optimize this at all. I want the code to be readable, and so I'm going to do something really horrendous and create a vector of the floating point values, which represents all of the pixels surrounding the pixel I'm currently investigating over this 5x5 area. And all I'm doing is extracting those pixels in my neighbourhood and pushing them into the vector. Once I've got 25 pixels in my vector, I then sort them using standard sort. Since I've got 25 pixels, the one in the middle, it will be at the 12th location of my vector. And that's what I'm choosing as my output value. It's pretty simple, huh? And so here in the demonstration program, I'm now running the median filter. And you might be at first thinking it's just blurring the image, but it's not. It kind of looks like it's painted it a little bit, so I'm sure median filtering is used in some of these arty effects programs. But I do have a test image that I've created here, where I've got the words median filter written on my page, and you can see the median filter has filtered out the lines because it sees those as anomalous, and it's also filtered out the dots. But there's sufficient information left in the text to then go and extract it using thresholding or morphological operations or something else. So it's just a precursory phase to help you with later stages of image processing. Once the dots get large enough that they occupy a region, in fact even so zoomed in like that, you really would struggle to identify the dots, but the text is just fine. So when you get this sporadic salt and pepper noise in your image, median filter is the thing to choose. Right, adaptive thresholds. This is the last one. I'm hoping this all still works. So bit 8, locally adaptive threshold. Not green. black. Bit 8. And finally, bit 8, locally adaptive threshold. I started this video by looking at a threshold. I started this video with bit 1 looking at thresholds that were applied globally across the image. More often than not, this is sufficient, but there are situations where you want to threshold an image based on local information. Working under the same principle as the median filter, we make an assumption that overall, for a small region of image, there's not going to be a great deal of spatial variance. So it's better to choose a threshold value based on the information in your locality, or at least bias towards a threshold value found from the information of your neighbours. So I know, for example, in this region of the image, if I take the average value of my neighbourhood, then things that are statistically interesting may be a certain level above that average. And that average might be different for different parts of the image. Which means if I used a global threshold, that threshold value may not be appropriate for different regions of the image. And locally adaptive thresholding, it may not be immediately obvious what locally adaptive thresholding is for, but I've certainly used it the most. It might not be immediately obvious what locally adaptive thresholding buys you compared to a global threshold. But I find it really useful when you've got change in luminance across your scene. Change in luminance is just a fancy word for shadows. The code for this algorithm is something we've started to see. We're now getting quite familiar with the code for these algorithms. We're going to iterate through all of the pixels, and in this case I'm going to take the average value of my immediate neighbours 5 by 5. But I'm then going to use that average as part of my thresholding calculation. Region Sun contains the average, but I'm going to bias that value with some user-defined constant, and that constant is user configurable via the user interface before we go on to threshold the image. So let's take a look. Here I've got the input and output showing just the regular threshold. This was the one we started with, bit 1, and I can try and find a value which sensibly thresholds the image, but you can see it's a global effect. And one of the things I wanted to show here is that the shadow cast by my hand is influencing that threshold decision. I'm going to press the 8 key now to choose the adaptive threshold, and we can see straight away the difference is that my shadow has basically become irrelevant to the scene. The local area around each pixel is used to guide what value we're using to threshold it against. And so the areas in shadow have overall lowered the threshold value, and the areas of brightness overall have raised the threshold value. And so we're choosing a value which is varying across the screen in order to make our thresholding decision. So if you wanted to make things that are shadow and luminance invariant, then you probably do need to use some sort of locally adaptive thresholding algorithm. It's also quite a cool visual effect too. I think that's it. Right, so now we need to do the outro. And so that's that. Image processing is a huge field, and for me I find it to be a very interesting one too. In this video we've had a very quick look, a very cursory introduction to some of the most fundamental techniques you need if you wanted to start doing image processing. As I mentioned in the introduction, you don't always have to work with images. Procedural generation may also employ a lot of these techniques too, particularly the morphological operations. Anyway, that's it for now. If you've enjoyed this video, give me a big thumbs up please, have a think about subscribing, come and have a chat on the Discord server, and I'll see you next time. Take care. And that's that. I think I covered everything. I've got all the code, so now it's getting ready for the edit, but I'm not going to edit immediately because it's been a long time. Probably do the edit tonight and I'll do that live. Fortunately also we didn't run out of sunlight, which I'm quite pleased about. The software all seems to have worked. I think the bit I'm concerned about is the morphological kernel stuff. I don't know how well that's going to come through. But I'm anticipating that this video will be quite a quick one, which is quite nice. So hopefully maybe get somewhere around 20 minutes, 25 minutes. We'll see. I was also a bit concerned, and we'll see how it plays out, but I've done it now. I can't go back and redo it, or I choose not to, about where to include the framework description. I did it sort of after the initial threshold value for bit 1, so I sort of introduced what a threshold was and then went to talk about other bits of code. I might try and edit that in such a way that the description of the program comes before the bits even start. Then again, I might not even include it at all. We'll have to see. I'll see how it pans out in the edit. Anyway, I think that means now that this particular video is over. I'll try and get this one uploaded as quickly as possible. I hope it's been an interesting look into what goes on behind the scenes. You can see it's not perfect. It does take a bit of trial and error to get right, and I'm a human being. I get nervous, and just like everybody else. So until then, take care. See you later.